Hey everyone, and welcome to this explainer. Look, if you're a junior developer trying to level up, or honestly, even if you've been around the block a few times but still find yourself wrestling with tangled, messy architecture, you are in exactly the right place. Today, I'm putting on my architect hat, and we're going to sit down together for a serious, deep dive code review. We're exploring the absolute bedrock of professional, object-oriented software design, the solid principles. And listen, we are not just talking abstract theory today. We're looking at real code, real refactors, and absolutely zero textbook fluff. Okay, let's dive right in. So let's start with a pretty blunt truth. Most developers out there, they can easily name the 5 principles. But very, very few can actually apply them under pressure when a massive deadline is looming. Knowing the acronym just isn't enough, right? Our goal today is to bridge that gap between theory and execution, literally line by line, so you can write code that actually survives contact with the real world. Here's our game plan for today's session. We'll start with the reality of messy code. Then we'll fix it by walking through SRP and OCP, move into mastering LSP and ISP, and untangle our dependencies with DIP. Finally, we'll bring all 5 principles together, and I'll wrap up with some practical advice you can take straight back to your desk. Section 1, the reality of messy code. We've all been there, haven't we? Have you ever worked in a codebase where a seemingly innocent bug fix in one feature inexplicably breaks 3 others? Or where adding a super simple feature requires you to hunt down and edit 10 different files? That, my friends, is a codebase without solid. It's basically a Jenga tower. You touch one block and the whole thing comes crashing down. Now contrast that with a solid codebase. Features are totally isolated. Tests are incredibly easy to write. New developers onboard fast because the code actually reads like well-structured prose, not a giant jigsaw puzzle. That's the exact kind of relief we're aiming for here. All right, moving to Section 2, fixing SRP and OCP. So let's tackle the single responsibility principle first. The absolutely crucial point here is that a class should have only one reason to change. Now, a huge misconception is that this means the class only does one thing. That's not quite right. What it actually means is that one stakeholder owns this class. Think about it. If your marketing team and your infrastructure team both need to request edits to the exact same class, you've got a violation. A great mental test for this: if you find yourself using the word "and" to describe what your class does, like, oh, it handles users and sends emails, it's definitely doing too much. You can usually smell an SRP violation long before you actually see it. Have you ever felt this pit of absolute dread when you have to open a specific class because you just know touching it affects the entire system? Yeah, that dread is a classic SRP smell. Other dead giveaways: class names ending in manager, handler, or helper, mostly because they tend to do a little bit of everything. You'll also spot methods way longer than 40 lines and import lists at the top of the file that look like a massive system architecture diagram. Consider a problematic user service that you'd find in so many real-world codebases. It validates input, hashes passwords with bcrypt, writes to the database, sends a welcome email, and writes to a log file. If the email provider changes or if validation rules tighten up, you are editing this one massive file. Now contrast that with a beautifully refactored architecture. We extract a validator, a password hasher, a user repository, and an email service. Our new user service doesn't do the heavy lifting anymore. It just orchestrates these elegantly isolated components. It tells a really clear story from top to bottom. And the best part, you can now test your validator without needing a live database. Okay, picture this scenario. You're working on a payment system that currently handles Stripe and PayPal perfectly. Out of nowhere, the product team bursts in and asks for Bitcoin payments. How do you handle that changing business requirement without breaking the code that's already running in production? Well, this brings us right to the open/closed principle. Your code should be open for extension, but closed for modification. Simply put, you should be able to add entirely new behaviors to your system without opening up and editing existing fully tested files. Every single time you open a file just to add another else if or switch case for a new feature, you are risking breaking what was already working perfectly. Here is how this plays out in code. An initial payment processing function is usually just a growing, ugly chain of if-else blocks. Adding crypto means editing this core function, which means you now have to rerun your Stripe and PayPal tests just in case you broke them. But if we fix this through abstraction, we create a payment processor interface. Stripe and PayPal get their own isolated processor classes. When Bitcoin is requested, it's a totally greenfield task. You just write a new crypto processor class. The caller function stays untouched forever, posing zero regression risk. It's a total game changer. Section 3. Mastering LSP and ISP. Now, the Liskov substitution principle sounds incredibly academic, I know. But the rule is actually very practical. If you replace a parent class object with a child class object and your program suddenly breaks or behaves unexpectedly, your hierarchy is dead wrong. Subclasses absolutely must be drop-in replacements. If your subclass overrides a method just to throw an exception saying, not supported, you've got an LSP violation on your hands. Think about this classic runtime bomb. We have a penguin that extends bird. But penguins can't fly, so the developer lazily overrides the fly method to throw an error. Later on, some innocent loop tries to make a flock of birds fly, hits the penguin, and bam, crashes the entire app. To fix this, we have to model what is actually true. We favor composition and correct hierarchies. We create a flying bird class that an eagle extends, while the penguin just extends the base bird class and only has a swim method. Now our flight function only accepts flying birds, and our runtime is perfectly safe. Next up is the interface segregation principle. The crux of this is that clients should never be forced to depend on methods they do not use. When you create these fat interfaces that lump together a dozen totally unrelated methods, you force classes to write empty stubs or return null for things they can't actually do. And let's be honest, having an empty stub in your class is essentially lying to the rest of your codebase about what that component is capable of. In a typical workforce management system, a giant worker interface might force a robot worker class to implement eat and sleep. The robot has no choice but to return null, making the entire system defensive because every caller now has to check if the result of eating is null. But if we split that fat interface into workable, human needs, and reportable, the architecture completely changes. The human implements all three, the robot only implements workable and reportable. The lying stops, the null returns vanish, and your code becomes dramatically simpler to mock and test. Section 4. Untangling dependencies with DIP. We're nearing the top of the pyramid here. DIP dictates that your high-level business logic should not reach down and directly glue itself to low-level infrastructure, like databases or email servers. Instead, both should depend on an abstraction, like an interface. The concrete implementation is then securely injected in. Listen, if you ever hear yourself or a teammate muttering, "Man, I can't test this easily," you are almost certainly looking at a DIP violation. The absolute biggest smell is seeing something like new concrete class, maybe a new SendGrid client deep inside your high-level service methods. When your unit tests fail because they can't reach a real email server, your domain logic is way too tightly coupled to the outside world. The solution relies entirely on injection. In a tightly coupled version, an order service directly instantiates its own SendGrid client. You literally cannot test this without sending out real emails. But in a refactored version, the order service simply receives an array of notifier interfaces through its constructor. It just loops through and calls notify. In production, sure, you pass it the real SendGrid class, but in your testing suite, you just inject a mock notifier. Boom, your business logic is now 100% testable instantly without a single network call. Section 5. All 5 principles together. All right, let's step back and look at the whole shebang. This is a synthesis of a realistic notification system using all 5 principles simultaneously. Because of SRP, we have perfectly focused formatter and logger classes. Because of OCP, if we want to add Slack alerts tomorrow, we just create a new class. The main service remains untouched. Because of LSP, our SMS and email channels are true drop-in substitutes. Thanks to ISP, our interfaces for sending and logging are tiny and highly specific. And finally, because of DIP, the core notification service knows absolutely nothing about Twilio or the file system. It's a modular, bulletproof system that is an absolute joy to work in. Section 6. The architect's final advice. So how do you actually build this into your muscle memory? First, pick just one principle per week and actively hunt for violations in your codebase. Second, do one small refactoring exercise weekly. Take a tangled function and isolate it. Third, keep solid in mind during your pull request reviews. Ask yourself, does this class have more than one reason to change? Fourth, please, don't over-engineer preemptively. Apply solid when you feel the friction of changing requirements, not on day one for a simple throwaway script. And finally, do yourself a favor and read Robert C. Martin's clean code. As you head back to your keyboards today, I want to leave you with one provocative final question. Are you writing code today that your future self, 6 months from now, at 2 a.m. on a Saturday during a massive outage, will actually thank you for? Keep solid in your toolkit, and the answer will be yes. Thanks for joining this explainer. I'll catch you next time.